All right. Well, I will. I will get started. Let me begin with a word of prayer. Dearly Father, we thank you for this day again. I thank you for this class and just ask you to guide our steps today. Help us to glorify what we do and understand a little bit more about linear transformations this morning, Lord. In your name I pray, Lord Jesus. Amen. Yeah, if you haven't turned in your homework already, hand it over so I can go get it. Thank you. All right, so I should begin here with a definition. We're going to talk about linear transformations today. And so, first up, here we go. Definition. If we have L, a mapping from, let's say, Rn to Rm is linear transformation. It's a linear transformation, or sometimes we call it linear map, if L of x plus y is L of x plus L of y, and L of cx is equal to CL of x for each x and y in Rn and C in R. So these two conditions I refer to respectively as additivity and homogeneity. So this character right here is the additive property, homogeneous. Although there doesn't seem to be widespread agreement on calling that the homogeneous property. There's at least some pushback on that from my brother. He doesn't like this term. But I've seen it in textbooks before, so it's not horrible. If you put these two things together, I just say you have linearity. So like, it would suffice to check the following. If we had L of, say, Cx plus y was equal to C L of x plus L of y, if we had that, right, for all x and y in Rn, and C and R. Like this right here, I would just refer to this as linearity of L. Now, the scope of this class, all right, is to study linear transformations primarily from Rn to Rm. But this concept of a linear transformation is far more general than that, right? Like, can you guys tell me some examples of linear transformations that are outside this context? How about the limit? If we have the limit of a constant times a function plus another function, we have a limit law, right? Pull out the constant, limit of f plus limit of g is the limit of cf plus g, right? So the limit is a linear operation. How about differentiation? Differentiation satisfies linearity, right? The derivative of the sum is the sum of the derivatives, and you can pull constants out, right? Definite integral. Again, linearity, right? If you've had differential equations already, the Laplace transform is a linear operator. I mean, there's so many things. The second derivative is a linear operator. And so I just used the word operator. Typically speaking, when we can also put here map or sometimes operator. If you use the word operator, typically what we have in mind there is that you're taking in a function and you're outputting another function, all right? So an operator is a mapping from functions to functions again. Function in, function out. But you've seen that already in like Calculus 1, right? The derivative is an operator. You input a function, get out a function. All right, anyway. Let us focus on the content here, though. What can we say about linear transformations? Let us start exposing their properties. So here's the way it's going to go, guys. Today I'm going to try to quickly derive all of the main theoretical achievements, if you will, of the linear transformation, and then we'll look at examples. All right. So one of the first things that comes to mind, of course, is that here's a proposition. Is that number one, L of 0 is equal to 0. So linear transformation maps 0 to 0. And number two, if we have a linear combination, say I equals 1 to n, well, let's not say n, let's say k, I equals 1 to k of ci vi, then that's equal to the sum I equals 1 to k of ci L of vi. So what I'm saying is that it maps 0 to 0, and the second equation I wrote, let me write that in an expanded notation so it makes more sense to you guys. Although we do want to get comfortable with the notation I just used for 2, right? So I don't prove everything in here, but here's a proof. For 1, what's 0? 0 is equal to 0 plus 0, right? So L of 0 is equal to L of 0 plus 0, which is equal to L of 0 plus L of 0, right? So therefore, L of 0 must be equal to 0. Subtract L of 0 from both sides of that equation, we immediately get the 0 has to map to 0. This is one of the fundamental properties of a linear transformation. Maybe the first thing I check if I'm in doubt about whether or not something's a linear transformation. If it maps 0 to 0, hey, there's a chance, right? Now this 2, number 2, I'm going to show you a proof by induction. So first of all, notice that L of C, C1 V1 is equal to C1 L of V1 by definition. So by definition of linear transformation, we can pull the constant out, right? So my claim is I'm going to give you a proof by induction on K. So K equals 1 is true. Suppose K true. And we'll consider L of the sum I equals 1 to K plus 1 of Ci Vi. All right, so that is L of, by definition, Ck plus 1, Vk plus 1, plus the sum I equals 1 to K of Ci Vi. I get all the way here in a second, guys. So for those of you who are in Math 200, I think there are a couple of you. There's at least one. There exists one. One is enough. If you could time travel to tomorrow, after tomorrow's lecture, this would make more sense. Because tomorrow in Math 200, I'll actually be talking about finite sums from an inductive perspective. Here we're just going to do it. So this is very, very silly. Like, how do you define the kth plus 1th sum here? Well, that's the kth sum, right, plus the next one. This just makes sense, right? That's actually how we define a finite sum, recursively. And so if that's the definition of finite sum, then I can use linearity, right? I get L of, I can pull the constant out, right? Ck plus 1, L of Vk plus 1, plus what? What I'm about to write in red, I'm going to use the so-called induction hypothesis here. So, going from the black to the red part is the induction hypothesis. The fact that I can break the addition of the two things into two things, L of two things, that is the definition of linearity. And then finishing below here, this is the sum I equals 1 to K plus 1 of Ci Vi, L of Vi. Was there a question? And that completes the proof, you see, because I've showed that if we know that the formula applies for k, it then likewise applies for k plus 1, right? Now, if I've lost some of you, I'm sorry about that, but I'll try to make it up for you with example 1, which is not really an example. But if I had L of C1 V1 plus C2 V2 plus C3 V3, how can we do that? We could say, well, that's really L of C1 V1 plus L of C2 V2 plus C3 V3, right? By the additivity. And then I can pull a constant out. And then I can pull the constant out over here and break up across that sum. So, I mean, if you look at it, you should be able to convince yourself that if we can pull constants out for one vector, we can pull them out for more. We can break across a sum of two vectors. We can break across a sum of three or more. All right, so that's that. So we're going to use this, right? That we can pull a summation out of a linear transformation. That's a critical observation that we want to keep using and not rederive. So we're going to talk about this once, but that's probably going to be it, theoretically speaking. And the next proposition and this is actually proposition 5.1.3. If you're tracking my notes here, is, oh man, let's let, so the notes are too general, annoyingly. So let's let V1, V2, Vk be a subset of Rn, and L a mapping from Rn to Rm linear. All right, then L, I need to come up, let me call you guys, what do you want me? I'm having trouble with words this morning. What should I call that set? You guys give me a name for it. What would you like to call this set here? Potato? That'll work. Potato. So L of the span of potato is the span of L of potato. So this begs the question, what do I mean by like L of S, by the way? This is by definition L of X such that X is an element of S, all right? So when I talk about L of potato, this is like all possible images. I mean, we can be more specific here. This is L of the span of V1 through Vk is equal to L, is equal to the span of L of V1 through L of Vk. So the, let me put it into words here. The image of a span is the span of the images. I'll repeat. The image of a span is the span of the images. These are the images of V1 through Vk under L. That's what that language means. All right. Now the proof of this is like pretty boring. Well, I don't know if it's boring, but it's easy. Proof goes like this. If we have L of the sum of Ci, Vi, I equals 1 to k, right? That's equal to the sum, I equals 1 to k, of Ci, L of Vi. So like, basically, here's the deal. This identity proves that these two sets are the same. See, because if I start with a linear combination, right, of vectors v1 through vk, that's one of these things, right? But then because of this identity, it's actually the sum over ci lvi like this, right? And this right here is an element of what? It's an element of the span of L of potato. Which I probably should just write it out what it is, because writing L of potato is about the same amount of writing as writing this, which is probably more instructive. But this is hilarious, so I'll leave that. Okay, anyway, so that's it. Like, linear transformation takes spans to spans. So the linear transformation of a span is the span of the linear transformations, of the image of the linear transformation under the spanning set. So, all right, there's that. So, question to you guys. What is a line? Do you have a description of a line? Yeah.
Well, a line has length but no width.
A length but no width. All right. How do we ever draw them? I mean, if they got no width, how can you see it?
Well, we have to. It's an undefinable.
Yeah, I know. It's kind of funny. Like if you listen to these kinds of geometric fundamentals, like they beg all the. It's like, well, how do we ever draw one if it has no width? Like, can't you? How could you even see it? You know? And yet we do. So. This is of course is not a line, because the other thing about a line is that it has this property of going on and on and on forever, right? This extension, but this would be like a line segment, right? So from P to Q, let's say, this would be a line segment, and so a line segment from P to Q, I don't seem to have a specific notation for. So I'm just going to invent one right now. So the line segment from P to Q, we could say it is P plus T times Q minus P, such that 0 is less than or equal to T less than or equal to 1. That's just, this is a standard trick. This is a parameterization of the line segment. See how this works? T equals to 0 gives us what? T equals to 1 gives us what? Plug T equal to 0 into this formula, what happens? You get P. Plug T equals 1 into it, we get P plus Q minus P, also known as Q, right? So this is the standard parameterization that goes from P to Q. It puts T equals to 0 here. It put T equals to 1 up here, and then T ranges between 0 and 1 between these 2 points. If I want to parameterize a line segment, this is my go-to formula. All right? I try to get Calculus 3 to learn this, but they resist me. They get like kicking and dragging and screaming. They resist me on learning this formula. I don't know why. Not all of them, but there's like a 30% that just refuses to learn this formula. But anyway, digressing. What would it take to get the lines to the line that extends? What would that be? If this is the the line that goes on and on from that includes P. So like suppose that we have the line segment is a subset of the whole line. What would the whole line be? How would you write a formula for that? What would it be? P plus what? How about this? P plus T times Q minus P, right? Such that what? If I want the whole line to just go on and on and on forever and ever, amen. This right here means subset, guys.
What is the symbol divided?
The what?
The symbol divided subset.
Oh, that's supposed to be a script L. I'm trying. Yeah. You can just make it a capital L if you want. It doesn't really matter. Yeah.
Such that T is a real number.
Oh, yes. T is a real number. Such that T is a real number. Exactly. So if we do that, we go on and on. That's it. This is a line. So how do you define, and like we could be a little bit more specific here. I could also talk about L equal to, say, P plus TV, such that T is an element of the reals, and P and V are in Rn. This here definition, this is gives line in Rn with base point P and direction vector V, right? Now, if I'm being careful, what do I have to assume about the direction vector? So I need what? I need V is not equal to 0 for this to be a line. Right? What happens if V equals to 0? What is that set? It's just a point, right? So a point's not a line. Although it'd be hard to tell the difference with the kind of description you were giving like 5 minutes ago, right? It's like just another thing that has no width or no... wait a minute, the line has no... I don't know, you come up with 3 different words for, depth, height, and width, and you say that the line doesn't have 2 of those, but it has extension in the remaining third, whatever word you're using. And then for a point, you say it has no extent in the length, any of 3 dimensions. Anyway, let us not reinvent Euclidean geometry this morning. No one cares. All right, any questions? So the reason I'm talking about this is I want to point out something to you, which is that a linear transformation, which we're going to call T for now, so like theorem, if T is linear transformation from Rn to Rm, and L is line, then T of L is, well, let me just write out what it is specifically. Assuming it has the same form above, you can easily see that what you'd get L of P, my bad, T of P, right, plus little t times big T of V, such that T is a real number, right? That thing I just wrote in black, what can you tell me about it? What is it? What is this? Is this not a line? This is a line. Base point what? T of P, right? And what? Direction vector what? What's the direction vector? T of V, right? So what is that? I mean, is that a line? Is T of a line a line? Is the image of a line under a linear transformation, again, a line? The answer is maybe. Why do I say maybe? The reason I say maybe is because we don't know, in general, whether or not t of v is going to be not zero, right? If t of v is non-zero, it's a line, but if t of v is 0, not a line, right? It could possibly squish a line to a point, right? This could happen. So, there's a similar theorem which says that a linear transformation maps line segments to line segments, right? It maps line segments to line segments, or it squishes line segments to points. So like, let's just look at a simple example of that. We can look at the unit square, 0, 0, 1, 0, 1, 1, 0, 1, right? That's the unit square. And we'll look at t of x comma y equal to, I don't know. Let us do like 2x minus 2y and then x minus y. All right? So let's see what happens. T of 0, 0, where does it map? Where's t of 1, 0 map? Where's t of 1, 1 map? Where's t of 0, 1 map? So you guys help me out here. T of 0, 0 is still 0. Very good. By the way, I am assuming this is a linear transformation. All right? You could prove it, though. I don't recommend that at the moment. We're going to find a much easier way to check it's a linear transformation here in about 3 seconds. So let's wait on that. All right. Okay, so yeah, 0, 0. Where's 1, 0 go to? 2, 2, 1. Where does 1, 1 go to? 0, 0. And where does 0, 1 go to? Negative 1. All right. So let's see here. If I draw myself some axes down here. Let me attempt a picture. So we go, this line segment, 0, 0, 0, 0, 1, I'm going to use red, right? Call that L1. Where does that get mapped to? It maps from 0, 0 to where? To 2, 1. So like here. So this is T of L1 is the red segment. This is L1. How about this one? 0, 0 to 0, 1. This one over here. Let's call that L2. So we start out at 0, 0, and we map to 0, 1, which goes to minus 2, minus 1, which is like over here, right? This is T of L2, right? What happens to what happens to this one? Which we could call L3, for instance. That goes where? That goes, L3 goes from 0, 1, 0 to 1, 1, which maps to from 2, 1, right? This point right here is 2, 1. So it maps from here back to there, right? Now I can draw some orientation on here just to keep track of things. So if I maintain the sense of, you can see easily that the orientation of the line segment's preserved as well, if you think about it. What's left? Up here, right, if we go, say, from, like I call that L4, going from 1, 1 to 1, 0. We're going then like this back here. So the image of every line segment, right? The image of every line segment here is a line segment, right? And I'd love to say that the image of a square is again like kind of like a square, but that doesn't actually seem to happen, does it? Because it turns out that the range of this linear transformation, apparently where's the range of this linear transformation going? Apparently it looks like it's all along this line, right? And you could kind of see that more directly by simply looking at this. This is x minus y, right? The quantity times the vector 2, 1, right? So basically, it's just sending out a scalar multiple of 2, 1. That's what this map does. It maps you along over 2, up 1. All right, let me move on here. So how do we decide? I got more of these kind of things to talk about, but what is the simple algebraic test for linearity? How do we do this? And there's basically just a theorem here which says the following: L from Rn to Rm is linear transformation if and only if L of x is equal to Ax for some A in R n by m rather. M as in mommy, n as in nanu. So this theorem, which is sometimes called the fundamental theorem of linear algebra, but not always. There's a disagreement about what the fundamental theorem of linear algebra is in different textbooks, but I had once upon a time a textbook which called this the fundamental theorem of linear algebra, but whatever. So the proof of this we should talk about. Here's the proof. If L of x is equal to Ax, right? Then if we have L of Cx plus y, that's A times Cx plus y, right? But that's C times Ax plus Ay, which, by the way, is equal to C times L of x plus L of y. So when I have an if and only if, this if, let me trade this out for a symbol like this that kind of shows you better what's going on here. So what I've showed you at the moment is this direction of the proof. If I assume that there's a matrix which gives you the formula for the linear transformation, well, for a function, then it follows that that function has to be a linear transformation, see? And the proof is just properties of matrix multiplication, just like that. All right? So that's the one direction. Sorry, I try not to bring one direction into this. But that joke is fortunately losing understanding, which is a good thing. When that joke fades into obscurity, society will be better. But the forward direction here, if, so like suppose L from Rn to Rm is linear map, all right? Then notice x is equal to a sum I equals 1 to n of x sub I, e sub I, where, using E1 equals to 1, 0, 0, etc., right? We can expand a column vector in terms of the standard basis, right? But if this is a linear map we also have the formula that we can pull the summation out of the formula for the linear transformation. So what's that give me? That gives me that L of x, right, is equal to L of the sum I equals 1 to n of x sub I, e sub I, all right, which is the sum I equals 1 to n. Pull the constant x sub I out, and I've got L of ei. But what is this? What is this formula? Well, we know what this formula is because we studied matrix multiplication as a weighted sum of column vectors. So I can rewrite this expression right here for the following matrix multiplication. This is nothing more than L of E1 L of En times the vector x1, x2, xn. All right. In other words, let us just call this thing right here, let's recognize what it is. This is a matrix A, which is in Rm by n. And this formula is literally Ax. So this shows you that if we have a linear transformation, we can rewrite the formula as matrix multiplication. And not just that, actually, there's more here. This choice of matrix, is there more than one matrix which would work? No. Like, look at the derivation. The matrix is uniquely specified by its action on the standard basis. There is one and only one matrix which satisfies this role. And for that reason, we make a definition. We're going to call this matrix the so-called standard matrix of L. The standard matrix of L. So before I move on to the next board, let's cycle back to example 2, and let's prove that that's a linear transformation. How do we do it? Rather t. T of xy is what? My claim is that it's t of E1, which is, by the way, 0, 1, my 1, 0. T of 1, 0, t of 0, 1, times xy, right? That's the claim. So this is, we just calculated them, 2, 1, minus 2, minus 1, times xy. That is, here's our notation. We use brackets t. This is the standard matrix of t. By the way, the reason that we should not be surprised after we gain maturity of understanding about this chapter, the reason that squished a box to a line segment, right? The reason that it squished the area of the area of this square is 1, right? What's the area of this? What's the area of a line segment? 0, right? There's a reason for that. What can you tell me about this matrix right here? Is it invertible? What could you calculate now that we learned them? Determinant. What's the determinant of that matrix? 0. Not an accident, right? Not an accident at all. So here's a definition for us, guys. Definition, given linear map T from Rn to Rm, the standard matrix of T is brackets T, and by definition that's T of E1, T of E2, T of En. This is the standard matrix of a linear transformation. And with respect to that standard matrix, the formula for t is just t of x is equal to standard matrix of t times x. Simple as that. All right? So in the world of all possible functions, like the linear transformations are really, really nice, the way they work. At this point, I think I should share with you my cavalcade of examples of linear transformations, because basically what I have in the notes here is a whole slew of examples, where I've done exactly what I did in example 2, which is to study what happens to a given, what happens to a given linear, happens to the unit square when we map it under a given linear transformation. And I even have some like higher dimensional examples. So let me show you if I can get this thing going. Oh, I seem to have forgot my my attendance sheet today, so I guess I'll top hat for. I know you got to have your top hat, right? Well, it always seems like it takes longer to boot up when I'm waiting for it, you know? You ever notice that?
Isn't that usually how technology works?
Yeah, how it doesn't work, exactly. Let's see here. If I can find... All right, well, I got it. We're getting closer. Yeah, here we go. All right. I think I forgot my laser, which is sad, but we'll deal. So we're in chapter 5, and see if this works here. Oh, unfortunately, oh man, well, that is annoying. I apparently have opened the version of it that's not compiled well. If the internet's working, we'll be okay. Give me a second here. Did you guys have a good weekend? Yes, no, sort of. Pretty good. My weekend was going pretty well, and then I went to La Carreta. I love La Carreta, don't get me wrong. But you guys ever been to the La Carreta between, over on Timberlake, like close to Lowe's? So I went there, and then we were driving 2 cars, and so I parked in the Lowe's parking lot because, it was Sunday afternoon, so it was pretty packed, right? And then my wife, she parked the van in the way back of La Carreta, which is fine. Then we switched vehicles, right? Which is, in and of itself not particularly interesting. And then afterwards I forgot that I was driving the van, so I went back to Lowe's, right? And I don't know if you ever noticed, but there's a slight incline between the La Carreta parking lot and the Lowe's parking lot. There's like a little slope there. And so I went up it. It was fine. I didn't think anything of it. Then I came back and went down it. And about halfway down, I was telling my daughter, be careful, it's slip. And words had not come out of my mouth before I was on the ground. And it turns out that when you fall that distance after a certain age, it starts to really hurt. So that's my exciting story for the weekend. All right, so here's an example. Here we have the linear transformation x to y. So what's this do? It doesn't do anything to x, and it just takes y and it stretches it out, right? So we take the unit square, it becomes a rectangle. Notice that the matrix here, if you could write it out, it would be 1, 0, 0, 2. The determinant is equal to 2 here. Not an accident that the area is twice the original area. If we were to look at the linear transformation defined by, rescaling in times k, in both the x and the y directions. It's just, I mean, if k is bigger than 1, it does like this, right? What's the area of this? The area of this is k squared. What's the area of that? 1. What's the determinant of the matrix? K squared. So k squared, so the area of that times the determinant of L is equal to the area of this. That happened. Another example. This one here, oh man, that's annoying. So it's just minus 1s, right? So all that does is that sometimes, like we'll study that in geometry, that's inversion, right? So that took, these are the same size, it's just my scaling's different, right? So this unit square flipped back over. Notice that the determinant is 1. So the area, again, wasn't changed. It's actually determinant 1 suggests that the area before and after, same area. This one here, 1, 2, 3, 4, does something a little bit more funky. This is kind of more generally what happens with the linear transformation in the plane, is it takes the square and it squishes it into some kind of parallelogram. If you could calculate the area of this parallelogram, what you'd find it was is 2. And you'd also find that, well, there's something to say about the orientation of that versus that. It disorients the box. That's a -2. The determinant of A is -2. This right here is a nice matrix. This is an orthogonal matrix because the columns are perpendicular in length 1. Right? The vector 1, 1 and the vector -1, 1, these are perpendicular. And because I've got that 1/√2, they're actually both length 1. This is an orthogonal matrix. This one is actually just a rotation. I told you guys before that orthogonal matrices are rotations. Well, no, I didn't say that. I think in here I said that a rotation is an example of an orthogonal transformation. But in fact, well, I guess this is just an example of that, I suppose. Again, the area is the same before and after, right? Because the determinant of that linear transformation is 1. So, this one here, we've got, it's kind of the same one as before, but instead of dividing by 1/√2, we don't. In this case, the matrix, the square gets blown up, actually. See, now it's got side length square root of 2. So the area of this box is 2. Not an accident, the determinant of that matrix is 2. I don't have all of these determinant comments in the notes, so I'm adding something here if you're paying attention. We can do a general rotation. Let me move on here. This one is just, though this is very boring. This is the identity transformation. If you multiply by the identity matrix, is that. This one here is more exciting because this one squishes. This one squishes the like that, I think. So that's that one. And of course, you could also project the other way, like so. You know, you can think of it like that. I think these are just mappings from R2 to R2 to R1 there, if I did it right. Maybe not. My bad. My pictures. Anyway, I think I'm just about out of time here, or really out of time. I also have, eventually in here, an attempt at some 3-dimensional pictures. You could see here's the 3-dimensional one that takes this cube and squishes it onto the parallelogram. Again, we're dropping from 3 dimensions to 2 dimensions because the determinant is actually 0 for that one. But anyway, see you guys Wednesday. Thank you, thank you.